Transistor biasings. Now there's an amplifier and amplifying the signal. Now it is required that only magnitude of the input signal should be increased, and there should not be any distortion and the output signal. This is the requirement of the good amplifier, that only we want to increase the amplitude, and we do not want any distortion the output signal. Okay, this is what is required. So this is a faithful amplification. Faithful amplification means exactly the output signal of the same shape as that of the input signal, only it is strengthened now. To get the faithful amplification, we have to ensure, like, there are two junctions in a transistor, input junction and output junction, and first junction should remain forward biased during the signal processing, and output junction should remain reverse biased during the processing of the signal. This is the requirement for the faithful amplification. This is known as the transistor biasing. Should be such that only magnitude of the input signal should increase and no change. There should not be change in the shape. To get the faithful amplification, input junction should be forward bias, output junction should be the reverse bias. So first we have to study the DC load line, how the load line is obtained. This is an NPN transistor. Okay, emitter is grounded, connected to the zero potential, earth potential. Collector is connected to the load resistance through the reverse biasing. Okay, and connected with positive mean reverse biasing. Thus battery is called VCC. The collector current is flowing in a direction shown in the figure. The voltage here is VCE between collector and emitter, and shown here is also the VCE. That's the emitter current. Here is the base terminal. There is no signal now. No signal is applied, but the base is connected to the forward biased with the help of the battery VBB. Okay. Now, what is the voltage here across the load is ICRL, and let me again draw the RL and the battery. Here the voltage between this point and grounded VCE. Now this is negative, positive, positive, negative again. Thus the net voltage VCE becomes VCC minus ICRL because of the opposite sign, minus plus and again plus minus. Now just rearranging, and now we get the value of IC from this equation. So IC comes out equals to minus 1 over RL into VCE plus VCC upon RL. This is a very important equation. And comparing this equation with the equation of a straight line, y equals to mx plus c. So with y it is IC with m minus 1 over RL, with c is VCC over RL. M is the slope of the line, and here it is equals to minus 1 over RL, means the slope is negative. So this slope is negative, and if we draw a graph between x and y, that's with negative slope, this is a line, straight line, having a constant slope. Similarly now in our case, like this is the equation, the same equation rewritten. Now if we let the VCE equals to 0, and then we get the value of IC, VCE decreasing along this side, and here VCE equals to 0, and here IC is equals to VCC over RL. So this is the one point, and for second point we again rewrite the equation, And what we do here, let IC equals to 0. So substituting, and we are getting the value of VCE becomes VCC. So here the IC 0 and here the VCE equals to VCC. This is the point, joining the 2 points, we are getting a line that is called the load line. This is a load line. The straight line is called the load line. And in the output characteristics having the base current, some value, let that value is 5 microampere. IB is equals to 5 microampere, it is say, for this particular, characteristics curve. And where it intersects with the load line, that point is called the Q point or the quiescent point, shown with the red dot. So this is shown with the red dot. This is our the Q point. This point is called the Q point. It's very, very important. And here you draw the perpendicular, one on x-axis, one on y-axis, the O to C, O to D, and with the Q point, that's called the operating point. This point should be properly chosen because it's very important for the faithful amplification. And with 0 input signal, this Q point decides the value of the VCE with the 0, OC volt, and the collector current is OD, milliampere, it is milliampere. So with Q point there is a particular VCE and particular collector current, and Q point should be, it should be at the middle of the load line for the faithful amplification of the signal. It should be at the middle of the line. It should be properly chosen. So it should be at the middle of the line. Okay. So it is clear from the following figures. So this is a figure, you just note down the red points. This is cutoff region, along this is cutoff. There's a saturation. Active region is between the, cutoff and saturation. That's active region. And Q point should be between the 2 red dots for the faithful reproduction of the signal. Okay. So this is very important, the Q point should be in the active region. Now here you note down the Q point is not at the center of the load line, but it is very near the saturation. If it is near the saturation, this is how the, the signal current is varying. Like the base current is varying, signal is applied to the base. The base current is varying like this. So with the variation of the base current, similarly the collector current varies, but collector current gets cut off because of the signal goes to the saturation. Here it is good, the same, but here it is cut off. And here the collector emitter voltage varies like this, and again it is clipped. And this is the same, but it is clipped along one side. So this is not the good, chosen. And now second, if the Q point in here cut off, again there's a cutoff region and signal is varying like this, like the base current of the signal is varying like this. And what happens, the collector current varies accordingly. This is good, same, but here is cut off. The collector current gets cut off because it's going to the cutoff region, and here it is the collector current gets cut off. This is the same, okay, but here this is cut off, clipped. So this is not again the good by choosing the Q point near cut off. And if the Q point is chosen at the middle of the load line, this is very good. The base current is varying as collector current is varying too, and base current is varying, collector current is varying too, base current is varying, and now the collector emitter voltage is varying in the same way, and same way the signal is exactly reproduced and strengthened. But now let's suppose that the input signal is of the large amplitude. Now the Q point is chosen at the middle, but even then the base current is going to the saturation, some value going to saturation, there is a clipped, and again the collector emitter voltage is also clipped, and some position of the base current is going into cutoff. So that's why the here the collector current gets clipped, and similarly the collector ammeter voltage gets also clipped. So this is again not good. So input signal should be weak. The strong input signal, even chosen the Q point at the middle, but it will not be good. So input signal should be the very small. So the important points for the proper biasing, we should be it should be taken into care that establish the Q point, which is the operating point in the center of the active region. It should be in the center of the active region. Q point should be center of the active region. Stabilize the collector current against the temperature variation. And input signal should be very small, as we just seen the above case. Okay, fine. Now important points for proper biasing. Now we will discuss the various points which are taken into account for the faithful reproduction of the input signal. Operating point of the Q point should be in the middle of the load line. It should be in the middle of the load line, or you can say in the center of the active region of the characteristics shown below in the diagram. The characteristics, so that on applying the input signal, it should reproduced applying the input signal, the instantaneous operating point means the variation of the operating point it should not move either in the saturation region, or it should not move in the cutoff region. So it should remain in the middle, in the active region. So if it will go in a saturation or cutoff, the signal will be clipped. So this is a requirement, for faithful reproduction, that Q point should remain at the center of the active region of the characteristics. This is a very, very important point, and the biasing techniques are based on this principle, on this point. Like this here, it is at the center of the characteristics curve. So this is cutoff region, here's the saturation region. The signal is not going in saturation or cutoff, so that's why it is exactly reproduced. So the Q point is at the center. Now stabilize the collector current. Collector current decides the Q point. Collector current is related to the Q point, But collector current is sensitive to temperature. It is sensitive to temperature. So if the collector current changes with temperature, the position of the Q point will also change. And there will be a fear that if it go in saturation or cutoff, the signal will get distortion, signal will be distorted then. The self-destruction of the unstabilized transistor is known as the thermal runaway. So if the transistor, if the transistor is burned out if the transistor is burned out for excessive collector current, then it is called thermal runaway. This is a current equation that the current due to majority carrier is beta IB and leakage current is ICEO. ICEO means the leakage current collected to ammeter when the base is open. Okay, this is collector current complete equation. The majority current and minority current. So, and it is found that if the temperature increases by 10 degrees Celsius, then almost it doubles the collector current. Collector current is sensitive to temperature, It doubles the leakage current, It doubles the leakage current. The 10 degrees Celsius doubles the leakage current. So with the rise in temperature, the leakage current will increase. As the leakage current increases, it is in addition with beta IB, the IC will also increase. If IC increase, when the IC will increase. If the IC increases, the increased IC will further raise the temperature, will become responsible for raising the temperature of the transistor. And as the temperature of the transistor further increases, which implies in turn will increase the leakage current. Leakage current again will increase the collector current, and it becomes a loop. So this effect is cumulative. Cumulative means it comes in loop and collector current will go on increasing till the transistor gets excessive heating. Collector current becomes very large, causing the transistors to burn out with the very large collector current. And the value of the beta and VBE are not exactly the same for the two transistors. Even the two transistors are of the same number, even then beta and VBE they never match exactly. There's not exactly matching of the two values, beta and VBE of the two transistors, even of the same number. There's hardly any exactly matching. So if a transistor is replaced by another one, even of the same number, what happens? The beta will change. If the beta changes, the Q point will shift. And again, there will be a fear that if the Q point comes in the cutoff region or in the saturation region, then again the signal will be distorted then. So that's why the need of the biasing circuits. So these are the problems So to hold the IC constant, irrespective of the internal parameters of the transistors, irrespective of the individual variation in the transistor parameters, irrespective of the individual variation in the transistor parameters. So that's why we are defining the stability factor. Stability factor is defined as the ratio of how the collector current changes, with respect to the leakage current. Here the leakage current which we are talking, it is the collector ICBO, leakage current collector to base when the emitter is open. ICO mean ICBO, and at the constant value of IB and beta. So stability factor is how IC changes with the change in the leakage current that flows collector to base when emitter is open. Okay. So this is the IC equation. This is the IC equation. ICEO and ICBO are related with this equation. ICEO is equals to 1 plus beta into ICBO. Substituting there, IC equals to beta IB plus 1 plus beta into ICBO. Now differentiating for this relation between ICEO and ICBO, you just see my previous videos in my channel, Electronic Physics and Spirituality. You see my video that's for the leakage current, So differentiating now with respect to IC, we are just differentiating with respect to IC. DIC or DIC is 1. So because S is DIC over DIC BO. Now from here we find the stability factor S. We are calculating S from here, and it's a very, very important relation for the further discussion of the biasing circuits. Okay, thank you, and please subscribe my channel if you feel good then. Now important point.